Let's move to the next section. Let's talk about software-defined network in Yang, one of my favorite topics. Again, we receive a very good contribution from JASPAR. Let me introduce our speaker, Izumi-san and Ito-san. Tatsuya Izumi is a group manager at Automotive R&D division at Sumitomo Electric Industries. He started as a researcher for in-vehicle networks in an architecture. Recently, he's developing network products, including Ethernet. Further, he's contributing to .1 and JASPAR and to define the automotive TSN profile. Yoshihiro Ito, he is an academic member of the JASPAR Next Generation High-Speed Network group. Since 2001, he is an associate professor at the Nagoya Institute of Technology. Formerly, he worked at the telecom industry at KDDI. So welcome back again to the stage. The floor is yours.
Thomas-san, thank you for your kind introduction. Good afternoon, everyone. I'm Tatsuya Izumi from Sumitomo Electric and JASPAR. Before presentation, let me introduce us a little more. The speakers, I and Ito-san, are the representatives of JASPAR, the technical consortium of Japanese OEM and suppliers. And the co-authors, Nomura-san from Honda and Goto-san from Toyota, are listening to this presentation with you as audience here. So let's get started. We want to discuss the automotive SDN architecture for enabling SDV. This is the agenda of today. Our presentation consists of 3 parts. At first, we'll show you the background and the objectives, and then we'll focus on study of the automotive SDN, and finally, we'll show our future works. So let's start it. Slide 3 and 4, the introduction to JASPAR and our working group. But these slides have already explained another JASPAR presentation this morning. So we'll skip to explain. In this Tech Day, there are 2 presentations from JASPAR. Our working group is composed of 4 teams and sub-teams. And I'm the leader of the SDN Study and Verification team. And this is our presentation. So let's get started explanation on the background. As you know, the keyword automotive SDN has become hot recently. So in this Tech Day, the SDN session was set up also. JASPAR has advocated the concept of in-vehicle SDN since 2017 to realize the dynamic configuration of in-vehicle Ethernet. A study of JASPAR's use case is proceeding under the leadership of the OEM, and we actively gave presentation at IEEE PA.1 DG and Tech Day 2022. In this way, JASPAR was the first in the world to raise the concept of the automotive SDN, and we want to start considering the architecture with it taking the lead. So, as background for introducing SDN, we'll explain the SDV, software-defined vehicle. As you know, SDV means the vehicle that can continue to evolve with the software update. Comparing the before and after of SDV, from the viewpoint of the vehicle of usage of vehicle and network, not SDV has no function updates after shipping. So it was sufficient to implement a free equipped design in the development stage. On the other hand, SDV is updated daily as a smartphone. So it is necessary to have software and hardware mechanism ready for future updates. In addition, redesign and reconfiguration are required in conjunction with function updates. So to realize SDV, in addition to a flexible software platform, such as ODA, hardware and networks must have a mechanism that enables function updates. In this presentation, we focus on the networks. So back to the agenda, we finished the background of objectives. So we explain the study of the Automotive SDN, the main topic of this presentation. First, we'll introduce JASPAR's automotive use case and roadmap. And then we'll explain the functional requirements for Automotive SDN. And finally, we propose JASPAR's architecture. So we'll introduce the use cases where SDN can be expected to apply. This slide shows 3 examples, such as a software update like OTA, and a hardware update, example plug and play, and a fail operational system. For ODA, we illustrate two application examples. One is while downloading software. We can shorten the download time by temporarily changing configuration, such as a bandwidth. Another example is to optimize the configuration as traffic amount change after update. For hardware update, use cases such as upgrading from manual to autonomous driving by retrofitting the ECUs and software sensors, we can allow the new traffic between the added ECU and the existing ECU by updating flow table. For fail operational systems, when some failure occurs while driving, we can avoid the communication failure by rerouting. So we want to say that since SDN has a high affinity with the evolution of SDV, it will significantly increase the added value of cards. So next, we explain the existing technologies, ICT field trends. Until now, setting configuration and updating have been carried out for each network device. SDN that can dynamically update configuration through centralized controls is gradually being put to practical use. So the advantage of SDN is reduced workload and quick configuration change. But the biggest disadvantage is high processing load on the controller. In this way, the concept of SDN is useful, but it isn't easy to apply the technology of the ICT field directly to vehicles. So JASPAR is considering the architecture suitable for the in-vehicle use. This slide shows the JASPAR's automotive SDN roadmap. The horizontal axis shows the generation, and the verification axis maps the function and the corresponding technologies. In the future, it would be ideal for updating dynamically and in real time, like in the ICT field. But we believe it isn't easy to achieve this in vehicle system in one step. So we have set 2 factors that are likely have a huge impact to SDN. The one factor is how to change the configuration, whether select from preset configurations or configure by dynamic calculation. The another factor is when to change configuration. whether vehicle is stopped or during runtime. Based on these two factors, in introducing SDN, we called SDN version 1 by starting the straightforward method, selecting from the preset configurations. So the operation will be as static as possible for the time being. And we plan to step up gradually SDN version 2 and version 3. So now, let me introduce how to proceed with the architecture study. There are two phases. One is the requirements analysis, and the other is the architecture study. In requirements analysis, we start the analysis from SDV to SDN, and then we determine the assumed scenario from the typical use case. At last, we define the basic requirements from common items of multiple assumed scenarios. After that, in the architecture study, based on the analysis of the current architecture, such as the in-vehicle or ICT field, we studied on the in-vehicle architecture as JASPAR's proposal. And then we'll embody the architecture in order of the requirements to study logical and physical architecture. In summary, we define the basic requirements of in-vehicle SDN from the upper level of requirements, SDV, and study the in-vehicle architecture suitable for the basic requirements. So we start the analysis of the upper requirements. This is the repeat of the last year Tech Day. The image of the SDV defined by JASPAR is, in addition to being reprogrammable by OTA, the car can switch configuration according to user's request and context without software reprogramming. Here, context means the state where the vehicle driver are replaced, and it can change frequently and reversibly. So the SDV can support the large-scale upgrade by OTA and the dynamic configuration according to the context. In this presentation, we scoped the network so the switch configuration is equivalent to the switch network configuration. Next, we break down the requirements analysis from SDV to SDN. So the SDN has a mechanism that can switch network configuration according to user requests and context without reprogramming. To make it more specific, we will study requirements by applying them to concrete use case scenario that I have explained, such as plug and play and ODA. So today the time is limited, so we show only one example, configuration change after plug and play. In a system where ECUs are connected via multiple Ethernet switches, we consider use cases that support additional communications when pre-mount ECU is added. So our assumed scenario as follows. First, connect an additional ECU free port. This is a trigger for the SDN, start of SDN. And collect topology and application information of the whole network. And then, based on these informations, derive the appropriate network configuration and apply it to each Ethernet switch. So after that, a new communication path is established between the existing ECU and additional ECU. Note that blue parts, so such as a trigger, correct information, derive configuration, and apply configuration are the common scenario and do not depend on the use case. So we define the basic requirements for automotive SDN based on the assumed use cases. The summarized common requirements are summarized as follows. First, trigger acceptance is to detect trigger of configuration change. Second, information collection and configuration derivation is to derive the appropriate network configuration according to the network topology and application demands. And third, the reflection of the configuration is to reflect the derived network configuration to the Ethernet switches. So we JASPAR believe that these are the basic requirements for automotive SDN. So next topic is the architecture study. We start the comparison of the existing architecture. One is the conventional in-vehicle network device, non-SDN switch, and the other is the SDN-supported network devices in the ICT field, example, OpenFlow. So the conventional devices cover the data forwarding, control, and application, so that it completes control within each switch. So that we call this the autonomous distributed network control. In contrast, SDN-supported network device separate from control and forwarding function. So the SDN controller collects the information from the whole network and centrally control switches. So we call this the centralized network control. In distributed network control, devices operate based on a fixed network configuration input during start of production. So the multiple switch work individually with no controller. So all switches need to be reprogrammed every time network configuration is changed. On the other hand, in centralized network control, at receiving the unknown flow, switch asks the controller, and the controller derives a new network configuration by dynamic calculation. So since the processing load on the controller is large, so it is unsuitable for the automotive use. And no automotive switch ICs supports OpenFlow. In this way, existing architecture have several issues. So it isn't easy to apply this technology to in-vehicle directly. So it is necessary to consider an architecture suitable for automotive use to deal with the above issues. The one answer is the hybrid architecture of JASPAR's proposal. The feature of this architecture is to combine the distributed and centralized network control. The basic action is the same as the distributed one, which works with the preset fixed configuration. But the difference is that the multiple network configuration are held in advance. And the controller selects a new configuration based on the external trigger. So only selection within the preset configuration, and there are no need to the dynamic calculation. So it leads to the reduction of the processing load on the controller. And in addition, if it covers within the preset configuration, there are no need to reprogram. So it leads to the reduction of the reprogramming for configuration change. So we believe that it's an architecture that keeps the advantage of the centralized control and compensates for its disadvantage by combined distributed one. So breaking down the functional requirements for more detailed one, and we try to classify the functional requirements, whether distributed or centralized. Shown in this table, the trigger acceptance and the information collection is classified as centralized, and configuration derivation and reflection are classified as distributed and centralized. This slide shows the role of the SDN system. So based on the functional requirements on the previous slide. First, detect the trigger of the SDN execution and from the other systems, such as the dealer systems and the OTS system. Next, collect the topology information and software configuration, and based on this, select the appropriate configuration from the multiple configurations. At last, reflect the configuration to each Ethernet switch. This slide shows the logical architecture for the SDN version 1. Since the use cases, the other system already have the topology information and software configuration, we defined two inevitable functions, such as the SDN controller and the configuration reflection function. So the SDN controller function select an appropriate configuration and instruct this function to change the switch released parameters. So the SDN configuration reflection function is change the parameters according to the request from the SDN controller. So next, we show the physical architecture when the SDN version 1 is applied to central and zonal architecture. In this case, SDN controller function is placed in the central ECU, and the network configuration of the zonal ECU is centrally managed. Once the configuration is reflected, the switching function of each zonal ECU works autonomously. So we finished the study of the Automotive SDN, and finally, we'll show you our future works, verification by POC. This slide shows the configuration of the POC system currently planned. As I explained earlier, we plan to implement the control and data transmission function. In controller function, Linux-based OS is installed on the single-board computer, such as Raspberry Pi, and application is implemented. For data transmission function, since the lower layer of the SDN is based on the 802.1 TSN standard, it will be realized by the automotive switch IC board. This POC aims to verify the feasibility of the architecture quickly. So it consists of the combination of the commercial available boards. However, in cooperation with the switch IC vendor, automotive products are selected from the vital switch IC. So we show the evaluation plan. Our evaluation items are the verification of the flow of the function, and the processing time, and the amount of traffic for SDN control, resources, and so on. The results of our verification will be fed back to the functional requirements and architecture for SDN version 1, and will be published as the JASPAR's standard document, March 2024. So we want to finalize our presentation by summarize. So to realize SDV, dealing with the trinity of software, hardware, and networks is essential. Automotive SDN is the general term of the four technologies that can dynamically change the configuration and function of the networks. It is highly compatible with the evolution of SDV and can coexist with the existing technologies. It isn't easy to directly apply SDN technology in the ICT field to vehicles. So JASPAR is studying the architecture suitable for the automotive use. This presentation proposes a novel hybrid architecture that combines the advantage of distributed and centralized network control. After proof by POC, the result will be published as the JASPAR's standard document, March 2024. So that's all for today. If you have any questions, please speak slow and clear, And short question is welcome. Thank you for your kind attention.
So thank you very much for this very, very interesting presentation. The publication will be public to JASPAR members or will be public for the rest of the world as well?
All members, not JASPAR, not only JASPAR. Yeah.
Okay, wonderful. Are there some questions? Yes, please.
Very interesting talk, thank you, very relevant, I think. I wonder, the approach that you have multiple configurations at SOP, considering that you have many variants of vehicles, do you think it's scalable, and do you think you can pre-compute those configurations for some use cases? It's something that I wonder.
So thank you for the good question. As you talked, it's not easy to preset configuration, but some configuration is preset in the start of production, and other configuration is the update by the OTA, but the frequency of the OTA is reduced, we think so.
Okay, thank you.
Additional questions? Yes, please, Alan.
Hey, this is Vlad Microchip. I like what you're doing. This is very exciting and interesting. I think you said that OpenFlow SDN implementation is difficult and complex, and that brings two questions. First, what is the complexity? Just for my own education. And the second one, is this the problem you're planning to solve in future, or it's so complex that it's not even feasible to attack it in the context of automotive? Thank you.
Thank you for the question. So I think, so in order to realize our concept, we divide so dynamic configuration and static configuration. So and then we use both of dynamic and static configuration. So by using two concepts, dynamic configuration and static configuration, we can realize our SDV. Is it your?
Yes, my question was on the complexity of the OpenFlow, because I think you dismissed OpenFlow because it's too complex and it cannot be done at runtime, and that's, you started talking about the pre-calculated configurations. So my question is, what is the complexity? How big is it?
I think so. You're correct. It's a very complex, complex program. So we at first start a very simple configuration, and then we will make our configuration more complex, and try to confirm my strategy. Okay. So I think you are correct. So it's very difficult problem to solve. So we try at very small, simple configuration.
Thank you very much.
Next.
Yeah, so this is Bernie from NXP. Okay, so I understand basically, at a startup and also at when a car stops, you need to basically do the reconfiguration. I'm more interested on the configure at real time. So specifically, like what happens, like a lot of your configuration is very static. Like once you add an ECU or you add new features, you go off and reconfigure the switch. All that is fine. Well, what happens, for example, if there's a link failure and all of a sudden you need to reroute traffic to a different path and you have to reconfigure this? Like, are you taking care of that as well? And what is the latency before you actually get around that fault? And the other thing I was going to mention, there's in the standards, there's things like CB. I'm not sure if you guys are actually even thinking of that at all. I know it doesn't apply in all scenarios, but I'm just curious currently what you do upon a link failure.
So, thank you for your question. I think so. There are many. So there are too many solutions we must solve. So there are many ways to realize our concept. So we must search the most appropriate one. But we think it takes a long time to find the solutions. So we try to we continue to try. So we try to study our SDV. Yes.
Okay, I understand. So basically, it's not something that you're currently looking at. It's something that you may look in the future as you learn more, I guess, about SDN. Is that like?
All right. Thank you. I think we can continue also outside the discussion to understand better what the gentleman is asking specifically. Further questions? So I do have a question. I'm a little bit worried about plug and play and additional easy use. What are the use cases of this easy use post SOP? I have a little bit difficulties to imagine what kind of easy use this might be. Have an example?
One example is from upgrading from manual driving to autonomous driving by retrofitting the ECUs and sensors. So the autonomous driving from level 2 to level 3 and level 4 upgrading by the plug and play.
Okay, understood. All right. So thank you very much again for your very interesting contribution. Thank you.
Thank you.
Thank you very much.